Ampere's circuital law and its applications. Ampere's circuital law in electromagnetism is analogous to Gauss's theorem. In electrostatics. In electrostatics, what did we have? We had a Gaussian surface. This was a Gaussian surface. And we had charges inside. We had charges Q1, Q2, Q3, say Q4 is outside. Then here in electrostatics, Gauss said net flux to the surface is net enclosed charge, that is Q1 plus Q2 plus Q3 by epsilon naught. This was Gauss's theorem, which states that the net flux to the Gaussian surface is total enclosed charge. Here we are not going to consider Q4 because Q4 is outside. This is outside the Gaussian surface. It is outside the Gaussian surface. So net flux is total enclosed charge by epsilon naught. Now, Ampere's circuital theorem tells us, here what was my flux? Flux was E dot ds. Ampere's circuital theorem tells us that if we have a closed path, and within the closed path, say we have currents flowing in, I1, I2, say this is I3 outside. Here, Ampere's circuital theorem tells us that the line integral of the magnetic field, this is B dot dl, around any closed path. Gauss's theorem was over a surface. This is along a closed path. That was in a surface. This is along a closed path. Is equal to. This was net charge. This was summation of all the enclosed charge by epsilon naught. Here this will be mu naught times the total current, the net current. Here the net current inside is I1 plus I2. I3 will not be included because I3 is outside, like here Q4 was not included, Q4 is outside. So this is what Gauss's theorem was in electrostatics, and Ampere's circuital theorem is in electromagnetism. It is in electromagnetism. They are more or less analogous. Here this was the net flux, that is summation of E dot ds. This was summation of E dot ds. This is summation of B dot dl, that is ds, and this is dl. That was 1 by epsilon naught. This is mu naught in the numerator. There we had epsilon naught in the denominator. And this is mu naught, permeability of free space, in the numerator. There it was enclosed charge within the Gaussian surface. Here it is enclosed current within the closed path. Here we have the closed path. So if we can write down Ampere's circuital theorem, we can write it in this way. Ampere's circuital theorem states that the line integral of the magnetic field or magnetic field can also be known as magnetic flux density be around any closed path it should be a closed path is equal to mu naught times the net current I threading through the area enclosed by the path. That is, line integration of B dot dl is mu naught times the net current threading through that loop, threading through that path, where mu naught is known as permeability of free space, where mu naught is known as permeability of free space. Now, Ampere's law can be used as an alternative of Barth-Savart's law to calculate more easily the magnetic field due to a current carrying conductor. It can be used as an alternative of Barth-Savart's law. But the problem here is, children, it can only be done when the current carrying conductors have a high degree of symmetry. That means you can calculate for an infinite wire. You can take it as an alternative of Barth-Savart law. Barth-Savart law, remember, for a finite wire, it was a big derivation. Then why should we use Barth-Savart law? Barth-Savart law can be used for finite wires. And when your wire is an infinite one, it is better to use Ampere's circuital theorem, because here you can do this in a much simpler way, in a much easy way. But there is one assumption, that there should be a high degree of symmetry. There should be, that means you can apply it for infinite wires. Now let us apply this Ampere's circuital theorem we are going to apply this Ampere circuital applications of Ampere's circuital theorem Let us apply this for some cases to study. But remember, children, this can only be done for infinite wires because it should have a high degree of symmetry. You can apply this. This is a much easier method, but not always. It can replace Barth-Savart law only when the wires are infinite. You cannot do it for finite wires. You cannot do it for finite wires because in that case, the symmetry won't be there. The symmetry won't be there. Now, first one, we are going to find out the magnetic field due to an infinite current carrying wire. Magnetic field due to an infinite current carrying wire. Now, in Barth-Savage's law, we have done for an infinite wire. This was what we have done. Remember, we did it for a finite wire. Phi 1 and phi 2 were the angles. This was an expression, a big derivation. And then we, for an infinite wire, we have put phi 1 equal to phi 2 equal to 90 degree. Because when the wire was infinite, phi 1 and phi 2 tended to 90 degree. This was the magnetic field expression mu naught I by 2 pi r. Now, if you are asked only for an infinite wire, then no need of going through Barth-Savage's law if not mentioned otherwise. If you are asked to find the magnetic field for an infinite wire only, then directly do it with Ampere's circuital theorem. If you are not asked to do from Barth-Savage's law, then you can skip this huge derivation. So we are going to find out the magnetic field for an infinite wire using Ampere's circuital theorem. Now say we have an infinite wire. And this is my closed path. This is my infinite wire carrying current I. Let XY be my infinite wire carrying current I. This has the radius R. This is my closed path. Now let us assume a small length over here, dl. Let us assume a small length over here, dl. Now, according to Ampere's circuital theorem, look here, according to Ampere's circuital theorem, line integration of B dot dl over a closed path is mu naught times the net current threading through the loop. So here if we can apply this, line integration of B dot dl is mu naught times the net current is I threading through this loop. Now the only problem lies here is how to do B dot dl, because we have to know the angle between B and dl. Now you use the palm rule and find out the magnetic field at this point due to find out the direction of the magnetic field due to the current carrying I at this point. Now if you use the palm rule, you see the magnetic field is along this direction, along the direction of dl. It is at right angles to R. So this is the direction of B, and B and dl are in the same direction. So the angle theta between B and dl is 0. Once again use palm rule and find the magnetic field at this point. See if you can take a circular loop and the current is going through here, or if you can take this as a circular loop and say the current is going through here, then at this point current is going up, and this is my circular loop. Then at this point my magnetic field, use palm rule. Use palm rule. Thumb in the direction of current, fingers to the point, perpendicular to the palm. Perpendicular to the palm is along this direction. So DL and B are in the same direction. Here DL and B are in the same direction. So if you can do B dot DL, it is line integration of B DL cos 0 is mu naught times the net current. This is B into line integration of DL is mu naught times the net current within that loop. And if you add DL, 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 what do you get? You get the circumference. So B into 2 pi R is mu naught I. So what is the magnetic field now? It is mu naught I by 2 pi R. It is mu naught I by 2 pi R. If you remember from Barth-Savart law, we came to the same expression, mu naught I by 2 pi R, but it was a big step. Ampere's circuital theorem cannot be applied for finite wires. You can only apply for infinite wire. So if you are asked for infinite wire only, then you can directly do it with Ampere's circuital theorem, which is a much smaller method, easier method of doing it. Now let us find out the magnetic field for an infinite long solenoid. Let us find out the magnetic field due to an infinite long solenoid by Ampere's circuital theorem. Magnetic field of a long straight current carrying solenoid. Now, if you consider a solenoid, say we are drawing the cross-sectional part. Say the current carrying wire is coming out from here and going in the other side. The wire is coming out from here and going in the other side. It is a long solenoid. This is the current is coming out from here. Dot means out, cross means in. Now, what are the directions of the magnetic lines of force? Direction of the magnetic field lines. If you take the palm rule, the current is coming out from there and going in the other side. It is coming out from here and going in the other side. The thumb will give you the direction of the magnetic lines of force. So the magnetic lines of force will be like this. A solenoid behaves like a bar magnet, we know. It behaves like a bar magnet. These are the lines of force inside. The lines of force has a direction by the palm rule. It has a direction this side. This is the direction of the magnetic lines of force. Now we have to take a closed loop. Now let us take a closed loop over here, because Bart-Savart law can be applied to a closed path only. This is a closed path. Let these points be A, B, come from A to B, B to C, C to D, and D back to A. Now what is Ampere's circuital theorem? Ampere's circuital theorem is line integration of B dot dl is mu naught times the net current. So if we apply over here line integration of B dot dl over the closed path A, B, C, D, A is mu naught times the net current within that loop. Now can you tell me what is the net current within this loop? Say these are the number of turns, right? These are the number of turns. You have the number of turns here. Current is coming out from here and going in that side. It is coming out from here and going in that side. Let the number of turns per unit length in the solenoid be small n. That means the number of turns which are going through the solenoid per unit length be n. Therefore in AB length, what is the number of turns? It is n into AB. And see, each wire carries current I. Each wire carries current I. So what is the current through this loop? Through this loop you have so many number of turns and each wire carries current I. So my net current is N AB into I. This is my net current. So this is my net current. So this can be written as mu naught into N into AB into I. I is the current through each wire. N is the number of turns per unit length, and in AB length within that loop, number of turns is N into AB, and in each wire the current is I. So my enclosed current, the enclosed number of the total net current threading through this loop is AB into I into N. N is the number of turns per unit length. Now we are left with to find out B dot dl. Now when you are doing out B dot dl in the closed path, here children, magnetic field due to the solenoid is in this direction and dl is in this direction. If you take a small length dl, it is in this direction. So this part theta is 0 degree. Angle between magnetic field and dl is along AB is 0. For this part for AD, this angle between magnetic field and the loop, theta is 90 degree. Again for BC, magnetic field is in this direction. This is the lines of force direction. Here angle is angle between B and the DL. DL is this. This is DL. This angle is 90 degree. And for CD, children, B itself is 0 because it is outside the magnetic field. So if we do B dot DL, if you break it into, this can be written as B dot DL over AB plus B dot DL over BC plus B dot DL over CD plus B dot DL over dA, and that is equal to mu naught n from here into AB into I. Now for AB, theta is 0. So when you do dot product, here theta is 0. For BC and AD, theta is 90 degree. And cos 90 is 0. For this one, again, theta is 90 degree. Cos 90 is 0. For CD, B itself is 0. Then for this part, B itself is 0. So this is 0. This term is 0. This term is 0. So you are left with only this term. You are left with only the first term. Only the first term is left. So if you write this is line integration of BDL over AB is equal to mu naught n AB into I. This comes from here. Now, if you add DL, DL, DL over AB, you get AB itself. B into AB is equal to, because integration of DL is AB. This comes from line in B DL, and if you integrate DL, it is AB. Mu naught n AB into I. Now AB cancels. So what is the magnetic field inside? Mu naught n I. Now if you look into this expression, children, mu naught is constant, n is the number of turns per unit length which is constant, I is the current through each wire, that is also constant. So magnetic field inside a current carrying solenoid is constant. That's what we know, that in a solenoid inside magnetic field is constant, which is mu naught Ni. Now, if you are asked to find the magnetic field here or due to a finite solenoid, then you have to use Barth-Savart law. This can only be applied if your solenoid is an infinite one and you find the magnetic field at somewhere inside where this has a huge symmetry. Now, if you find out the magnetic field by Barth-Savart law, you will find out that magnetic field here we got as mu naught Ni. At the ends, by Barth-Savart law, this cannot be found out by Ampere's circuital theorem. It will be mu naught Ni by 2. At the ends, the magnetic field becomes half of that which is inside. At the inside the magnetic field mu naught Ni, this is constant. And at the ends, it just becomes half of that is inside. And outside, what happens? Magnetic field decreases. So if you plot the graph of magnetic field versus the distance for this solenoid, say this is a solenoid. Let me draw this solenoid once again over here in a small scale. This is the solenoid. Say current is coming out from here, going in there, coming out from here, going in there, coming out from here, going in there. Now if you find the magnetic field due to this solenoid and plot a graph, let us plot a graph of this solenoid. Say this is the distance from one end. This is the distance from one end. And decide if we plot the magnetic field. Then the graph will look like this. In the center, the magnetic field is constant. This value is mu naught Ni. At the ends, the magnetic field becomes half. This is mu naught Ni by 2. This is mu naught Ni by 2. So the graph becomes, at the end, the magnetic field drops to half. The magnetic field drops to half. And outside if you go, the magnetic field will decrease. Outside if you go, the magnetic field will decrease. This is the nature of magnetic field of a long current carrying solenoid. Now center you can find out for a long solenoid. But if you have to find out the magnetic field at the ends or somewhere, if the solenoid is a finite one, then you have to apply Barth-Savart law. This can only be found out for a long current carrying straight solenoid. Next we move on to the magnetic field due to a current carrying toroid. Due to a current carrying toroid. Now what is a toroid? We are going to find out the magnetic field due to a current carrying toroid. Magnetic field inside the core of a toroidal. We are going to find out the magnetic field inside the core of a toroidal. Now what is a toroidal? A toroidal is something like this. Say this is a toroid and you have the wires, say, coming like this. You have a wire entering like this and then it goes the wires are wound and here the current goes out. This is a toroid. Let the toroid have a radius A. Say this is the center. I am not that good in drawing circles, so please try to understand this is the center, and here the radius of this toroid is A. Now we have to find the magnetic field. We have to find the magnetic field due to this toroid. Now if there are, now let us first write down the Ampere Circuital theorem. What is Ampere Circuital theorem? Line integration of B dot dl is mu naught times the net current inside. Now if you consider the current is coming out from here, if you draw the cross section, current is coming out from here and it is going inside. It is coming out from here and going inside here. Coming out from here and going inside here. So it's coming out from here, going inside here. Current is coming out from this side and then going inside the other side. This is the cross-sectional view. This is the cross-sectional view. Coming out, going in. Now, if we want to find the magnetic field outside, somewhere here, then here, if we draw the loop, which we have to draw this line integration, if you want to find the magnetic field outside, then this is my loop on which we have to integrate. So here, B dot dl outside, if you want to find out, what is your enclosed current within this green loop? Here, the amount of current which is coming out is equal to the current which is going in. Because here if the current is coming out as plus I, current which is going in is minus I. So for all points outside, your magnetic field, for all points outside, your magnetic field is 0. Why is it 0? Because amount of outside magnetic field is 0 because it's enclosed current for outside. Here, if all the wires carry current I, if all here, this is, here I current is coming out and I and minus I, we are going in. Here I is coming out, minus I is going in. So for outside, as well as on, till here, amount of current which is going in and amount of current which is going, amount of current which is coming out and in, they are cancelling each other. So net current is 0. So for B outside, if you want to find the B outside, here line integration of B dot dl is 0 because enclosed current is 0. Because amount of current which is coming out and amount of current which is coming in is, the net current is cancelling. Now we want to find out the magnetic field here. We want to find the magnetic field here. Now when you consider this brown loop, then this cross is outside the loop, just like Gauss's theorem. This cross is outside the loop, so we will consider only the current which is coming out. So if there are n number of turns, total current will be Ni. So in that case, if you apply B dot dl, B, the radius is A, integration of dl is 2 pi A. If you integrate dl, the radius is A. That is equal to mu naught times, if the total number of turns is n, and if each carries current I, then capital I can be written as Ni. I is the current through each wire and there are n number of turns. So total current is Ni. Here in between you have the same thing, only this radius will change. And inside, if you want to find out, somewhere inside if you want to find out the magnetic field. What is the magnetic field here inside? Here if you apply, here the enclosed current is 0 because neither the current is coming out or in here. Enclosed, there are no wires enclosed. So for inside, if you want to find out B inside, here B, line integration of B dot dl is mu naught times the net current inside, which is 0. No current. So from here B is 0. So for a toroid, if you are asked to draw the graph of magnetic field, for a toroid, if you draw a graph of magnetic field, if you are asked to draw the graph of magnetic field, now this is inside. Inside, your magnetic field is 0. Inside your magnetic field is 0. Inside the toroid, your magnetic field is 0. Now if you go in between there is a magnetic field. What is the magnetic field? Magnetic field is mu naught Ni divided by 2 pi A. What is A? A is your radius. So as radius increases, magnetic field will decrease. B is inversely proportional to A. So for minimum A, for here A is, the radius is minimum. For this one, the radius is minimum. Here R is minimum. And for this point, R is maximum. Now for B is inversely proportional to radius. So B is maximum when radius is minimum. From here to here B is 0 because net current enclosed is 0. Net current enclosed here is 0. As soon as you start from this point, what happens? What happens as radius increases from here to here? From this part to this part. In this part, what happens? Magnetic field is inversely proportional to radius. So as radius increases, magnetic field will decrease. So as radius increases, magnetic field decreases. So when radius is minimum, that is just here, radius is minimum, magnetic field is maximum. And as the radius increases, magnetic field decreases. And outside what happens? Magnetic field again becomes 0. This is how magnetic field changes for a toroid. Now if you have a long thick wire, let us find out the magnetic field due to a long thick wire. Say you have a long thick wire. Carrying current I. It carries net current flowing is I. Say this radius is capital R. Current is flowing in this direction. You have current coming. Current is flowing in this direction. Total current is I. It is uniformly flowing through the wire. Now I want the magnetic field somewhere at a point P1 outside. So if this is my loop, like Gauss's theorem at this point, line integration of B dot dl from Ampere's circuital theorem is mu naught times the net current. Here the enclosed current total is I. Now if this radius is small r, then B into 2 pi r is mu naught I. So magnetic field is mu naught I by 2 pi r. That is magnetic field varies inversely as r. As you go outside, B decreases with r. Now if you find the magnetic field on, if you want to find the magnetic field on at this point, say this is P2. Then this is your closed loop. This is your closed loop. In this case, line integration of B dot dl to this brown loop, again the total current flowing is I. Total current flowing is I. So B dot dl is mu naught times the net current. Here the radius is capital R. So B into 2 pi capital R is mu naught I. So what is your magnetic field? Mu naught I by 2 pi R. This is your magnetic field on, that is at P2. You're finding it at P2. This one was at P1. Now let us find the magnetic field somewhere inside a point, somewhere here, P3. Then your closed loop is this one. Now if you want to find out the magnetic field at P3, let this radius be small r. Now the enclosed current is only through this part. Enclosed current is only the part which is going through this orange part. The current which is going out of this loop will not be considered. You have to consider the enclosed current. So what happens? Line integration of B dot dl is mu naught times the net current I dash net current I dash. Now how do you get this I dash? How do you get this I dash? Now you do it by unitary method. Through an area of pi r square, my total current is capital I. Through an area pi r square, my total current is capital I. When the area is 1, my current is I by pi r square. And this is small r. So what is this radius? Through an area pi into small r square, this becomes I by pi r square into pi small r square. Now pi cancels. So what is your current? I by r square into r square. So this is your current flowing through it. Now, here this is I dash. This is I dash. So what we have to do now? We have to just put the value of I dash. So B into the radius is r, 2 pi r, is mu naught times I dash. This is I dash. Put the value of I dash. I by r square. Capital R is the radius of the full wire into r square. Now 1 r cancels. Therefore, magnetic field becomes mu naught by 2 pi r square into r into I. So you see here B is directly proportional to R inside. B inside is directly proportional to R. But B outside is inversely proportional to R. So if you plot the graph of magnetic field for this wire, if you plot the graph of magnetic field for this wire, this is inside. Inside, B is directly proportional to R, and outside, B is inversely proportional to R. So the graph will be like this. At the center, your R is 0, so magnetic field is 0. So the graph will be like this. At the center, my magnetic field is 0. Inside B is directly proportional to R, and outside B is inversely proportional to R. Outside B is inside the wire. Inside the wire, if you take this wire then and plot the magnetic field for this long thick wire, this is a thick wire, inside B is directly proportional to R. Directly proportional graph is this. At this point my R is 0. Now at this point your R is 0. At the center my R is 0, and therefore B is 0. Here B is directly proportional to R inside. Inside the wire, as R increases. Why? Because as R increases, your enclosed current will increase. Your enclosed current will increase. So magnetic field will increase. And outside what happens? B is inversely proportional to R. So this is the graph for a magnetic field of a long thick wire. But instead of a solid wire, if you have a hollow wire, then what will happen? If the wire is a hollow one, if the wire is a hollow wire, that means the graph will be like this. This wire is a hollow wire. So inside there is no current. Magnetic field inside is 0. Because if you consider a loop here or a loop here, my enclosed current is 0 because current is flowing only through this. Current is flowing only through this. So the graph will be modified inside, nothing else. it will be modified inside. The other part will remain the same. Inside your magnetic field will be 0 because there is no enclosed current, and outside it will be the same because the current enclosed, it will be the total current. Only inside it will vary. If it is a magnetic field, inside B is 0 and outside B will vary as R, because there won't be any change, because if you take a loop like this at the point P1, my enclosed current will be the total current I. Only inside, at it is a hollow one, therefore no current is flowing through this side. So inside magnetic field will be 0.